Okay, good morning and welcome to Lesson 1, Factor a polynomial completely and find the zeros. Our objectives are to factor a polynomial completely and then find the zeros of a factored polynomial. This is probably sounding somewhat familiar to you because we have been factoring and we have looked at zeros in the past. The difference in this lesson is that we're going to try to put together all of our skills, all of our tools into one problem. And we are going to walk through a step-by-step procedure in order to factor a polynomial completely. So let's look at what this actually means. So to factor completely means to continue factoring until no further factors can be found. And we did not do that in the past. We just used one technique and then we were done. So for example, when we factored out a GCF in one of our initial lessons, we just factored out the GCF and then we were done. But now we will continue to investigate the polynomial to see if it can continue to be factored. We've also done that with factoring out a quadratic. Sometimes we factor it out, but we could continue to factor it. So these are our steps that we're going to go through. The first thing we're going to do is search for a greatest common factor. If we find one, we're going to factor it out. And that's why we had a lesson on just GCF, so that you were comfortable and confident being able to do that. So that will always be our first step. We'll always look to see if we have a GCF. Step 2, then we examine what remains. We look for a trinomial or binomial, which can be factored. Remember that a trinomial is basically a quadratic, right? A 3 terms. It has 3 terms. Tri, like tricycle. It has 3 terms. A binomial has 2 terms. Bi means 2. And if you think about what we've done with binomials in the past, we factored those using difference of squares. So we use the sum and difference formula. So if we get a binomial, that would be something we would want to keep in the back of our heads. Is this a difference of squares? Can we continue to factor it? Step 3 is then, once we've factored it completely, we want to express the answer as the product, which means multiplication, of all the factors we find, including any GCF. So that's how we would write our final factored polynomial. So let's look at solving. Solving a polynomial means finding the roots, the x-intercepts, the zeros. We use all those terms interchangeably. You'll notice in this diagram here, you can see that to solve, if you think about these as x-intercepts, these are also considered the roots. And they're considered the zeros, remember, because along the x-axis here, y is always equal to 0. And you'll see here, to solve, step 1, set each x term equal to 0. That's why we call them zeros. We're setting the x term equal to 0 because that's what y is when we're here on the x-axis. And that's how we will find the x-intercepts. Once we have set each x term equal to 0, we just solve for x, and those will be our roots. And that's what we're going to do. Let's go ahead and practice a few examples. So what I have for you guys are 3 here, and then 2 on the next page that are a little more difficult, that require us to run through these steps multiple times. So let's go ahead and start with these. In this first example, remember that we want to first see if we have a GCF. And by now, some of you might be pretty good at doing this, and you can just look at it and find a GCF. If you still struggle a little bit with finding a GCF, then I would suggest going through how you did it in that first lesson. So 5x squared can be written as, and let's go ahead and write that out. So we have 5x squared can be written as 5 times x times x. 45 is the product of 5 times 9, but remember, we wouldn't want to write a 9 here because 9 can be broken down into 3 times 3. So we always need to break everything down into its prime numbers. So we have a 5 here and a 5 here. That becomes our GCF, and then we're left with x squared minus, because there's a minus here, minus 9. So that is one way we can do that. The other way is to look at your binomial and you think, what goes into both 5? What's the biggest thing that goes into 5 and 45? And I would say to myself, well, 5 goes into 5 and 5 goes into 45. And then I could just divide those out. So if I divide those out, that means I divide this side by 5, and I divide this side by 5, and that's what I will have that's left. So writing this with the GCF factored out, 5 is my GCF. If I factor out of 5, I'm left with x squared, and then negative 45 divided by 5 is negative 9. Okay, so either way is fine. If I did it this way in orange, I would still have my x squared here and my minus 9 from down here. So whatever way you're comfortable with. Normally we would be done. We factored out our GCF. But as the directions state, look at what we have remaining. We have a binomial here. This 5 is our GCF, so we're done with that. But we have a binomial of x squared minus 9. Can we factor that? Well, remember what I told you. Anytime we have a binomial, consider, is that a difference of squares? Is x squared a perfect square? Is 9 a perfect square? And it is, right? We can take the square root of x squared, and we can get x. We can take the square root of 9, and we can get 3. So we can write this second part as a difference of squares. So that's what I'm going to do here. I can't forget my GCF, so I've got 5. And then I'm going to write x squared minus 9 as x plus 3 and x minus 3. So now I look at what I have left, and I can't factor anything anymore. I still have two binomials, but these are factored completely. So I'm done factoring. Now we would go on to the next step. So let's solve. And then when we solve, if we remember our instructions, and we'll go back to those, it says set each x term equal to 0 and then solve for x. So we have two x terms, x plus 3 and x minus 3. I would set each of those equal to 0. So I will have x plus 3 equals 0. And then I would have x minus 3 equals 0. And then I would solve. So in this first case, I would have to subtract 3. So I would get x is equal to negative 3. And in the second case, I would just need to add 3. So I would get x is equal to positive 3. And this makes sense. This is a quadratic because it's squared. And I have two x-intercepts, two roots, two zeros. So my final answer, this is my quadratic in factored form. It's been completely factored. And here are my solutions. So I have factored and I have solved. All right, let's try the second example here. And let's see if we can do this efficiently. So first step is to find our greatest common factor. And I can tell that I'm not going to have any numbers that are greatest common factors because we have a 1 in front here and a 2 and a 15. But if I notice, I do have an x in every term, but I only have one x here, so the most I can take out is 1x. So I'm going to factor out an x. If I factor out an x here on the first term, I'm left with x squared. If I factor out an x here, I'm left with minus 2x. And for the third term, I'm left with minus 15. So now I have a trinomial. And one of the things we talked about was if we have a trinomial, we can maybe factor by grouping. We have that tool in our toolbox. So I would take the coefficient of my x squared, which is 1, times my constant term, which is negative 15. And that would leave me with negative 15 here. My middle term is negative 2. So what times what will give me negative 15 and then add to be negative 2? So if you think about that, 5 times 3, I know I can put a 5 here and I can put a 3 here because that gives me 15, but I need negative 15 and I also need a negative 2. So I'll make the 5 negative and that would work out. Negative 5 plus 3 is negative 2 and negative 5 times 3 is negative 15. So remember that I have my GCF here, can't forget it, but I'm going to go ahead and factor this quadratic now by grouping. So I'm going to rewrite it. So I'm going to rewrite it as x squared. Instead of my minus 2x, I split that term into minus 5x and plus 3x. And then I have my minus 15 on the end. So now I can group. So my first group, I have a greatest common factor of x, which leaves me with x minus 5. My second group, I have a greatest common factor of 3, which leaves me with x minus 5 again. I know that I have an x minus 5 in the first group and an x minus 5 in the second group, so I'm going to pull that out, which then leaves me with x plus 3. Okay, remember the very last step when you are factoring says to write everything, including your GCF, as a product. So I can't forget this x up here. I need to attach that back on. So now I have completely factored this, and my final step just said set each x term, so here we have an x term, equal to 0. Here we have an x term. This is a minus, I believe. So we have an x minus 5 equals 0, and then here we have an x term. So we have an x plus 3 equals 0. Well, this first one is already solved, x equals 0. On the second one, if we move the 5 over, we would get x equals 5. And on this last one, if we move the 3 over, we would get x equals negative 3. So we have 3 zeros, or x-intercepts, or roots. We have a 0, a 5, and a negative 3. And our final factored form, because this is part of our answer as well, is x times x minus 5, x plus 3. And notice again, we have a cubic because it's to the third power. So I would expect here that I would have 3 roots, and I do. All right, let's look at this third one over here. So again, I'm looking for a GCF, and I notice that on this one, I actually have numbers. So what number goes into 9, 6, and 3? Well, I think that I can pull out a 3 there. Then I look at my variables. I have 1x, 2x, 3x. Well, I can pull at least 1 out then. So 9 divided by 3 is 3. X squared divided by x, I'm left with x squared, or I should say x cubed divided by x, sorry. And then on my second term, I've got a plus here. 6 divided by 3 is 2. If I take out 1x from the x squared, I'm left with just 1. And then over here, a minus 3x divided by a 3x is just 1. Okay, now what I have here is another quadratic, so I would want to factor by grouping. I'm going to have 3 times negative 1 at the top. I'm going to have a 2 down here. And I know that 3 times a negative 1 will give me negative 3, and 3 plus negative 1 will give me 2. So writing that out, I'm going to have 3x squared. Instead of 2x, I now have plus 3x minus 1x, and then a minus 1. Looking at my grouping, I can pull out a 3x from the first part, which leaves me with x plus 1. Remember, these don't go away. 3x divided by 3x is just 1. And then here I can pull out a negative 1, which leaves me with a positive x and a positive 1. All right, almost done. So here I have an x plus 1 and x plus 1. That's how I know I did it correctly. I'm going to pull that out, and I'm left with 3x minus 1. But I can't forget about my GCF up front here, which was 3x. Okay, this is going to be a little bit different than what you've been doing, in that we're going to set each term equal to 0, but now we have a little bit more solving to do on this third one. So this first one, if I look at it, 3x equals 0, I divide by 3, 0 divided by 3 is still 0. So one of my roots is 0. X plus 1 is pretty easy. That would be x equals negative 1. But then here I have 3x minus 1 equals 0. So on this one, I'm going to first need to add 1 to both sides to get 3x equals 1. And then I will need to divide by 3 in order to solve for x. So divide this by 3, divide this by 3, and I would get x equals 1/3. So my root for this factor is actually 1/3. Okay, those are 3 good warm-up problems. I have 2 final remaining, so try to hang in there for these last 2, and you're going to see some patterns that we can go through that are a little more advanced. So again, let's look at this one. We need to factor out a GCF. A 2 goes into 2 and 32, so I'm going to factor that out. Looks like we have 1x here, 5 here, so I'm going to factor out an x. In this first term, I'm left with x to the 4th minus 16, right? 32x divided by 2x is just 16. So here again, we have a difference of squares. I can take the square root of x to the 4th, and I can take the square root of 16. So let's look at what happens when I do that. Square root of x to the 4th is x squared. The square root of 16 is 4. So my difference of squares is a sum and difference of x squared minus 4, x squared plus 4. So normally you might be tempted to stop here. But let's examine what we have. This binomial here, x squared minus 4, can I still take the square root of each term and get a perfect, is it a perfect square? Can I get a whole number? And the answer is yes, right? The square root of x squared is x, and the square root of 4 is 2. So I could continue to factor this binomial right here. This one, however, you cannot because it's plus. It's not a difference of squares. This is a plus, so this cannot be factored. So let's go ahead and factor this term and write our final answer. So this is going to factor into a sum and difference of x minus 2x plus 2. And then we still have our x squared plus 4 on the end. So now we have written this in factored form. Let's go ahead and solve for each x term. So the first one, 2x, that's pretty easy. 2x equals 0. We divide both sides by 2, and we would get x equals 0 still. The second one is also going to be pretty easy. You can just look at it and see that, hey, on that one, x is going to be equal to positive 2. And on this one, x is going to be equal to negative 2. But what about this third one here? We have x squared plus 4. Set that equal to 0. What happens? We subtract 4. We get x squared is equal to negative 4. Well, in order to get rid of the square root, in order to get rid of the square, we would take the square root of both sides. Square root of x squared is just x. But we cannot take the square root of a negative number and get a real 0. We cannot get a real x-intercept. So on this one, we would say we do not have any real roots with that one. Eventually, we'll be getting into complex roots, but not today. So for this problem here, our zeros, our roots are just 0, positive 2, and negative 2. And then we have 2 imaginary roots. Still for a total of 5, but we're not going to worry about those. Okay, good. So let's look at our final problem here. So in our final problem, we would look again at what can we do? Well, I don't see any number that's a greatest common factor, right? This is 9 times 5, which is 3 times 3 times 5. This does have a 3 in it. This one does not. This has a 5, but that one doesn't. This is just 2. So we can't pull any numbers out. We could, however, potentially factor by grouping because we have 4 terms. So we can factor this one by grouping. So on this one, it looks like I could pull a 4 out of both of these and an x squared. So I'm going to pull out a 4x squared. And then I'm left with 2x plus 5 here. On this one, it looks like this is 9 times 5, so we can write this as 3 times 3 times 5. This is 9 times 2, which is 3 times 3 times 2. So it looks like I have a 9 that I can pull out from both of these. So I'm going to pull out a negative 9, and I'm left with 2x plus 5. So again, back to our grouping. I have a 2x plus 5 here and a 2x plus 5 here, which leaves me with a 4x squared minus 9. Again, make sure we factored completely. This second term is a difference of squares. 4x squared is a perfect square, and so is 9. So I would want to make sure that I factored that one completely into 2x minus 3 and 2x plus 3. Okay, so this is our polynomial factored completely. And now for our final step, we would just want to find the zeros. So on this one, we have 2x plus 5 equals 0. Subtract 5 to the other side. We would have 2x equals negative 5. Divide by 2. X is equal to negative 5 halves. Can you start to see the pattern? The sign will always be the opposite, and then everything gets moved to the right side. So on this one, we have 2x minus 3 equals 0. We would add 3 to both sides. We would get 2x equals 3. Divide both sides by 2, and we would be left with x equals positive 3 halves. And in our final answer here, this looks just like this, only it's positive. So we know that this is going to be x equals negative 3 halves. Okay, that concludes our lesson on factoring completely and solving. So if you need to write the steps down, write the steps down. But the best way to do this is to practice it and to see it over and over again and get used to looking for a GCF, get used to looking at trinomials to see if you can factor by grouping, or look for difference of squares when you have binomials. So at the end of this lesson, hopefully you feel pretty good about factoring a polynomial completely, as well as finding all the zeros of a factored polynomial.